Okay, let's get started. So welcome to another ACM seminar. So we are happy to have Dr. Sangwoo Kang from KAIST, and he will be going to talking about sampling type imaging method for inverse scattering problem. So please welcome Sang.
Thank you for being here, and I appreciate the opportunity to make the presentation today. This is my outline. I talk about the background, about what is the meaning of the scattering problem and sampling type imaging method. And I talk about what is the governing equation and its related the 2D Ford scattering problem. And then I introduce the detail of what is the meaning of the direct sampling method. And finally, I'll talk about my 3 results about the limited view aperture problem, monostatic and bistatic configuration. First, background. We think about the scenario. There are 2 antennas, and transmitter antenna and receiver antenna, and there are some target. Then this antenna emits some source, something like acoustic wave or electromagnetic wave. Then these waves scattered by the target, we observe the data from this receiver antenna. It is called the scattered field. There are 2 types of the scattering problem. First one is forward scattering problem. Next one is an inverse scattering problem. The purpose of the forward scattering problem is to study about the blow-up property or some existence or some asymptotic formula of the scattered field from the information about the incident field and information about the target. On the other hand, the purpose of an inverse scattering problem is to retrieve the information about recover the information about the target from the incident field and scattered field. There are so many applications of the inverse scattering problem, such as the biomedical imaging for brain strokes and breast cancer detection, and non-destructive testing to identify the defect inside the wall or bridge. Also, it can be applied to ground penetrating radar. It's called the GPR, and synthetic aperture radar, and so on. My research goal is to deal with non-iterative imaging method in 2D and 3D time harmonic electromagnetic case. Because I studied the electrical engineering in my PhD. And also I tried to analyze the structure of the imaging method to understand the behavior and property of the imaging method and to explain the reason of observed phenomena. Finally, I want to develop the effective, also the good non-iterative imaging method to identify the target.
Are there any particular reason why you're focusing on non-iterative?
I'll talk about maybe 2 pages later. This is the figures of applications of inverse scattering problem. First figure shows the ground penetrating radar. This machine moving around across the ground, across the boundary. There are some antenna inside this machine. There are some transmitter antenna. Then scattered by target, we observe the data. From this data, we can detect some object during the ground. Next one is the NDT for crack finding. This is also same machine, almost the same machine. There are some antenna, receiver antenna, transmitter antenna. From the data, we can detecting the crack of the wall. Also, it is the brain stroke imaging. There are some antenna. There are for maybe 5 and 6 antenna. Then we can detect in the brain stroke. This is the breast cancer imaging. This is the antenna. Then we can detect the breast cancer from this data. Because right now, the traditional machine of the breast cancer imaging is to squeeze the real breast. So it is very hard to detect the breast cancer right now. So we try to apply the inverse scattering problem to real breast cancer imaging. The inverse scattering problem in physically, breast cancer imaging can be regarded the microwave imaging, which is used the frequency range from 300 megahertz to the 3 gigahertz. CT and MRI use the high frequency, so it is too expensive and heavy to carry and hard to fast image. Also, EIT use the low frequency, even though it is cheap, but it is hard to penetrate the object, such as the bone, like this one, because it is used low frequency. In microwave imaging, we use some middle frequency range, so it is low cost. It need only low cost, and it uses the safer non-ionizing radiation, and it have the ability to provide functional imaging without the use of the contrast agent in MRI. There are some inherent difficulty of the inverse scattering problem. In mathematically, it is non-linear and ill-conditioned problem. And so it is very hard to directly solve the problem. In physically, the data is scattered by the object, so structure of data is complex. To handle this difficulty, there are various imaging methods. I love this table from this article. This shows that there are so many numerical real algorithms. Then they apply to the numerical data, experimental data, human animal data, and clinical trial. Even though there are so many imaging methods, only these two imaging methods can be applied to the clinical trial. So we have to develop the good imaging method. The imaging method can be categorized the iterative method and non-iterative method. And iterative method can be regarded as the non-iterative Newton type imaging method. So we need a good initial guess and proper regularization procedure to prevent the local minimum phenomena. And it requires high computational cost and time. On the other hand, non-iterative imaging method require only low computational cost and fast, and it does not require a priori information about the object. Of course, the imaging quality of iterative method better than the non-iterative method. However, there are because of this advantage, I tried to study the non-iterative method.
You also mentioned about the memory issue.
Memory issue, what it means?
Iterative method requires only the low cost in terms of the memory, and the single iteration takes if I understand correctly, small amount of the computational cost per iteration.
Yeah, of course. But I mean that compared to the non-iterative method, the main part is the good initial guess, and this means that the good initial guess should including the prior information about the object. But in many cases, it is impossible. So that's one
quick follow-up question then. Yeah. Let me rephrase my question then. What method the state of the art is currently using between iterative versus non-iterative?
In my opinion, I think that this linear sampling method or factorization method are good compared to other ones.
So that non-iterative method is currently the state of the art comparing the both iterative and non-iterative. That is really being used in practice. In medical imaging, we mentioned some of them.
No, I don't think so. And because all of algorithm is the iterative type imaging method.
I see.
So I think that until now, there are no attempt to apply the non-iterative type imaging method to real application. But I think that since the iterative imaging method need good initial guess, so we can obtain the good initial guess from the non-iterative method. So there are so many non-iterative methods: direct sampling method, music algorithm, linear sampling method, factorization, migration timing method. But all these studies, almost many of these studies study under the ideal assumption, such as the multistatic, full-aperture, and many data. And this is the this scenario shows the iterative how the iterative and non-iterative imaging method detecting the object. Let's think about this receiver, and there are some transmitter. Then we can grid the region of interest. Then we choose for each sampling point, we calculate some indicator function. Then this indicator function blow at the sampling point if this point located inside of the object. So that's why we can detect the object from this indicator function. Among these the method I choose in this presentation, I choose the direct sampling method because it is very, very simple. The main advantage of the direct sampling method is it need only a few instant field. This means that we need only one or two transmitter antenna. Also, it does not require any additional operation, such as this is typo, singular value decomposition like music algorithms or linear sampling method. So it is very stable and strong to noise. And also, this direct sampling DSM is non-iterative type method, so it requires only low computational cost and time compared to iterative time method. Because of this main advantage, we can apply to this DSM in various configurations, such as limited aperture, monostatic, and bistatic configuration. I'll talk about what is meaning limited aperture, monostatic, and bistatic configuration later. Now I talk about the Govan equation. Yes. From the acoustic wave, we can see this wave equation, and from the simple separation variable technique, we can derive the Helmholtz equation. And this Helmholtz equation also derived from the electromagnetic wave. From the time harmonic vector equation, from the vector identity, we can reduce the vector Helmholtz equation. And in 2D transverse magnetic, this means that the only Z component is not equal to 0 and Hg equal 0. Magnetic field is 0. This means that physically, we think about the target is a long cylinder. Then only Z component is remained and other component is almost 0. So that's why this vector Helmholtz equation, we can think about just the scalar Helmholtz equation. Then Helmholtz equation explains the acoustic and 2D TM mode electromagnetic scattering problem. The classic to analyze the imaging method, we should know the structure of the scattered field and data. The classical theory of the scattering problem, there are some green, which call it a green representation theorem for exterior problem. Then this means that all solution can be expressed by singular value, depth layer, volume, potential. But it is not sufficient to explain the phenomenon and analyze the structure of the image method, because it is very hard to see where is the effect of the object, because there is only omega tau. So we need another representation formula.
Here U represents the location of the wave. Is that correct?
Yeah. And the shape or permittivity or something like that. To simplify the problem, I assume that the all target is small and well separate. Well separate means that there are no coupling effect, because if the two target is close located, there is a multiple scattering. So it is very hard problem. So we assume that the targets are well separate. And we use the notation of like this one. CM is the center, and alpha m is the size, and dm is the unit shape of the object. So like this one. And we assume that the wave is far field and plane wave. This means that the transmitter antenna and receiver antenna is located far from the object. Then this wave is almost plane. And from this notation and assumption, and we can define the piecewise constant function like the permittivity, step function, and wave number function. Then the total field U equals U instant field plus scattered field, satisfy the homologication with the transmission boundary condition and the Sommerfeld radiation condition. This means that the energy is fade out the mass of the object. Under this assumption and notation, the scattered field have this asymptotic formula. This means that scattered field can be expressed by the size and instant field and permeability and permittivity and the green function of the homologication. And where m is the polarization tensor of the target. In 2D and 3D, you can check the detail of the formula. Now we think let's study what is the meaning of the far field or plane wave. The electrical dipole antenna source express the green function form like this one, where the omega is the angular frequency, mu is the background permeability, and gk is the green function. The shape of the dipole is like in 2D. This is the like emitted at this point. But the green function have the far field approximation like this one. This means that the green function can be expressed by the exponential part. So this means that the dipole have the plane wave form, this plane wave form. So in this case, this wave is like the plane wave, real plane wave. From this, the assumption and notation, we call the far field pattern of the US like U infinite. Then this asymptotic formula can be reduced by this simple formula. This means that there is an exponential function like this one. This is the key part of my analysis. I'll talk about the detail of the introduction of the sampling time method. I'll talk about the DSM because, as I mentioned, it is very simple. The DSM for single impinging direction, this means that there are only one transmitter antenna. Then DSM defined like this one is very simple. And numerator term is by Helder inequality is just a normalization. And this is key part. And for multiple impinging direction, it is defined like maximum value. Where we know that this part is the far field approximation of the green function. This means that we test the data with the backpropagation value at each sampling point. If we check the data from the antenna to sampling point, then test and test. We can check the scenario by figures like this one. If the instant field like this one, we can measure the multiple at the multiple on the observation range. Then for next instant field, we can measure the data. Then the data can by matrix form, we can construct the full matrix like this one for full aperture problem. This is full aperture problem. Full view means that we only choose the instant field, only single instant field, but there are many observation directions. This is the analysis of DSM for single impinging direction. This means the full view and multi-static measurement. And we assume that the total number of observations n are sufficiently large. Then far-field pattern under the small volume and well-separated assumption, we can see the DSM. This indicator function have this expression. This is the size, permittivity, volume of the target, and instant field, and Bessel function.
Can you remind us what capital M represents?
M?
Capital M.
This means?
Yes, in the summation, the capital M.
This is total number of the target. M is the mth target.
Oh.
We assume that there are large M target, and this is the summation of each target. We recall the asymptotic structure of DSM. In this formula, the key part is the Bessel function. This is the simple figure of the Bessel function. Bessel function have maximum value at the center. This means that if searching point z is a searching point, sampling point, searching point equal to 0, searching point z equal to cm, they have the maximum. That's what it is why the DSM have maximum value at the center of the object. From this asymptotic structure, we can know the why there exists. We observe the unexpected artifact in the map of the DSM, because the oscillation property of the Bessel, this part generated the unexpected artifact in the result numerical simulation. Also, reconstruction quality of the DSM depending on the property of the object, something permittivity or size, like this one. As a result, there are some inherent limitation. If one of the target have large size or large permittivity value, then it has the maximum value at the point, but another target have low value in the result, then if this low value have almost the same to the oscillation value, then we can detect the object on. So it is the inherent limitation of this approach. Now I'll talk about the limited measurement configuration, some limited aperture, monostatic, bistatic configuration. Now we recall what is the meaning of the full view, limited view, monostatic, and bistatic configuration. Full view is the previous result. There are some transmitter antenna and there are multiple receivers antenna, and all the location of the antennas are fixed. And limited view is there is some instant field. We only measure the limited range. And monostatic and bistatic is the set of antenna are moving around the object. There's the transmitter antenna, receiver antenna are located the same position, and there is a transmitter emit some instant field. We observe the same position. And bistatic is some transmitter antenna, receiver antenna located another position, and this set of the antennas are moving around the object. Because the reason why I study the limited view or monostatic bistatic is in many real applications, it is impossible measure the data in full view. Data matrix. With respect to data matrix, we can compare the data. In multistatic, full aperture data is like this one, and full view is the only for fixed instant field. We choose the sum of column data. And limited view is sum of them is 0. We have no any data. 0 means that there is no data. And monostatic is the only diagonal part. And bistatic data is another data like this one. This means that compared to multistatic, ideal case, multistatic full-aperture case, there are some lack of information. So it is very hard to imaging the data by existing method. This is one of my results. In this result, I apply the DSM to limited view approach. From my analysis, we can find that DSM has this asymptotic expression. Until this part, it is same to the full view configuration. But this is the main part of our analysis. This is some theta n minus theta 1 is the range of the observation. And this can be expressed by infinite series of the Bessel functions and cosine and sine function. Let's see this animation. By depending on the range, this is blue line is just a Bessel function, and red line is like this function. As the range of detection is decreasing, this is increasing, and this means that the Bessel function part is the controlling factor, and large gamma S is the disturbing factor to detect the object. From this analysis, we try to find the range condition of the theta n, proper range condition theta 1, theta n, to make the gamma S equal to 0. So this means that equal to 0. So first case, theta n minus theta 1 is 2 pi. This means the full view. Then this is a cancellation. That's why the gamma S equal to 0. That's why we have the better result in full view problem. Also, theta n minus theta 1 larger than pi, we have the better result. Now, first, numerical simulation. The data is computed by FICO. That is the commercial software, electromagnetic simulation software. And we use the single frequency 1 gigahertz. And we assume that the background is vacuum. And we add the Gaussian random noise 20 dB by MATLAB. And region of interest like this one. And we consider only dielectric permittivity contrast case. The target permittivity of the target is 5 times of the background. And background permeability are the same to the magnetic permeability. In case 1, we consider the narrow case, and case 2, semicircular case, and finally we consider the wide case. This is a single object case. This black one is the transmitter direction, and red one is observation direction. Then, even though we use the narrow case, we can detect the object like this one. But of course, in semicircle or wide case, we can reduce the artifact in the result. Now we apply the multiple objects. In this case, in narrow case, we cannot detect the object properly, like this one. However, in case 2 and case 3, we can detect the object from the map of the numerical simulation. Even though we assume that the all target is small, we also apply the large object. In this case, even though we consider the wide range, we cannot properly detect the object by DSM. To handle this problem, I think that we need to apply multiple. So we also suggest the alternative or improved version of the numerical simulation version of the DSM, but I don't include the part this presentation. Now think about the monostatic configuration. Monostatic, I recall
in your previous slide.
Yep.
So in the top right seems to you have lots of measurement, but it seems to me that it's still hard to see from my eyes that how many obstacles you may have inside of the region. So in practical case, then how people utilize this method in search and
Yeah, of course.
target. Yes.
The DSM is successfully to the multiple small volume, small objects.
Even in this case,
if we extract just the value one, because this new version of the MATLAB, so it is very hard to the detection and the simulation. But if we choose the by value, we can find the real information of the target. It's a good question. Actually, the another disadvantage of the non-iterative method, where we should threshold the data.
Right.
Yeah, this is another main advantage or main issue.
And another question I have is, you consider the following scenario where one object is surrounded by another,
yeah,
so that maybe that objective is not really I don't know, have you considered that kind of scenario, whether the method you propose may
please.
So there's a center, in the center you have a small object,
yeah,
and there are many dense objects surrounded by that, and that satisfies all the assumptions you made. And have you tried that case, whether this method is successfully detects the one inside?
Yes, it is another good question, but right now I only consider the simple question is yes, another paper considered this scenario, and there are some open data like this scenario, your scenario, but right now I didn't apply this scenario.
Thank you. Maybe one more question. Have you tried with a different epsilon for different particle, different objective, so that?
Yeah, of course. Yeah.
And how the performance varies by that parameter? Because of course we have the background medium, and if the objective you might have is close to the background medium value, that might be super difficult to detect.
Yeah, you're right.
You're right. So I was wondering what would be the limit that this method can detect?
It's a good subject, but right now I didn't apply it. But you're right. If the background permittivity is almost the same to background, it is almost we cannot detect the object. Of course, yeah.
I just wondered have you ever tried?
Yeah, right now I have no idea what is the limitation of this permittivity.
Thank you.
Since the DSM applied to the only single impinging direction, we apply the DSM to monostatic wave, because look at this. Full view is have the same number of data of the monostatic wave, monostatic configuration. That's why we try to apply the DSM to monostatic configuration. But by applying the traditional DSM, we derive this asymptotic formula. This means that Z minus 2n. This means that we searching the target, not CM, only the 2C. So we suggest by simply adopt another indicate test function like this one, 2n, just the square of the test function. Then we find we derive this formula like this one. From this formula, we find this function, but from 2k0, this means that there are more oscillation, because this 2k0 is indicate the step of the Bessel function. This is the numerical simulation and the same configuration. And for small multiple object case, by DSM, we cannot detect it object. It has maximum value 2 times of the object, exactly 2 times of object, like this. But our MSM, we can detect it all object. Of course, there are so many oscillation compared to the full view problem. We also apply the large object case like this one. The center is like this one. And by MSM, we can detect the object like this one. But we can only recognize the center. We cannot detect the boundary. So it is another my future work. Recently, I tried to imaging the extend object with Monte Carlo simulation. Now, finally, we consider the bistatic configuration. Bistatic means that the receiver antenna and transmitter antenna, receiver antenna, and there's some on the range. And these set of the antenna are moving around the object. In this paper, we consider the perfectly conducting small crack, not the small object, small crack. And in this case, we suggest the bistatic sampling method like this one. We adopt another test function like this one. And from the structure analysis result, we can obtain this analysis. From this analysis, we can show that the indicator function depending on some range and size and target length and target location like this one. We have two observations. If var phi is equal to 0, this means that it is exactly same to the monostatic configuration because theta equals 0 is the same position instead. So in this case, from this simple property, this means that BSM is like this one. It is exactly same to the monostatic sampling method. Yeah, that's so from this observation, we can find that this is the extended version of the BSM, MS, monostatic sampling method. Another observation is the var pi equal to pi. In physically, I think that firstly, I think that the best range is just a pi because this is some transmitter and this is the receiver and this is located. It is best scenario to obtain the all information of the object. But from this asymptotic formula theoretical result, we can find that this is worst case. If var pi equal to pi, from this property, BSM is proportional to like this one. This is just constant. So if var pi is pi, the crack cannot be identified. This is a numerical simulation. We apply the same frequency, single frequency, and same noise and same ROI, but consider the perfectly electric conducting. So this means that the crack is metal and gamma 1, gamma 2, gamma 3 like this one. If var pi is the 360 degree, maybe 60 degree, we can successfully detecting the crack like this one. And if the var pi is pi over 2, then we can also detect it. And var pi is 2 pi over 3 is detected. And another ranges, we can also successfully detect objects. If var pi is pi, we cannot detect any cracks. This result. This is the worst result. And another observation is pi over 3 have the same result of the 5 pi over pi 3. And 3 pi over 2 equal to same to the pi over 2 also. So this means that based on the x-axis, the range plus range and minus range is. This is also identified from this observation. Yes, this is citation information to prevent the yes. Figure is from this information. Thank you.
Hey, thank you, Sangwoo. And are there any questions from the audience?
studied the non-iterative method, but I'm wondering that in limited measurement case, iterative method gives us good result or bad result, then non-iterative method is good. Then
I think that right now DSM is very simple. The reason why I use the DSM in this presentation is as you know, the BSM, DSM, or something like that is very, very simple. So that's why I talk about the BSM only simple method in this problem. But if we apply the another imaging method, we have to check it is work or not in a limited problem. Of course, also iterative imaging method result also can be used for the iterative imaging method by using the initial guess. Also.
Okay. Are there any questions?
What kind of initial guess do you need to interrogate?
It is depending on the problem. If actually another categorized by the imaging method is I don't remember exactly, but iterative imaging method reconstruct the not shape of the object. It is the reconstruct the permittivity like this one, background permittivity and inside permittivity. Then we can detect the object by this permittivity distribution. But non-iterative imaging method focus on the geometric information. Yes.
I do have a couple of questions, but I will ask just one or two. So, first of all, in your analysis, it's derived from some restrict assumptions on the scenarios.
Big assumption.
Yeah, and also your asymptotic term, the term you developed has an infinite summation. Then I wonder how do you carry it out in the numerical simulation?
Yes, of course. So this is another my object. In my another paper, I try to find what is the minimum or limitation number of the observation. Yeah. So I try to analyze this one, and yes, when I talk about this object to the engineer, they told me that they designed this real machine like some multiple number of observation, 16 or 32. And I tried to analyze this problem, and we found that not this sampling method, another sampling method in this case, the minimum number of the observation is just 8. But we have to put the data some opposite position, like if the antennas are not equidistributed, it is failed to the detecting data. But if we put the only 8 antenna like this one, we can successfully detect the object. Yes, question. Yeah,
that's one question.
Yeah.
Second one is I know that all the methods stemmed from the theoretical analysis, but in many practical problems does not really satisfy. I probably assume that it doesn't satisfy the assumption. So which means that your formula might not be accurate in many other cases. So have you tested out some other scenarios whether your method has?
Yeah, of course. Even though we didn't include this presentation, we also applied I'm right now I'm working with the real engineers, so they make the real machine, and they gave me some real data. We can check my asymptotic formula, even though we assume the small volume or well separate many number of observation. We can find that our method can perfectly detect the object. Yeah, even though our analysis have the limitation.
Right. Yes.
Technically speaking, yes, asymptotic assumption
can be done if your objects are sparse. But if that's not the case, people have already done the multi-scattering part.
Yeah.
For example, like
Yeah, of course.
usual scattering problem, you can account for as many multi-interactions as you want to. Maybe that can improve your result if those guys are close.
Yeah. Yes, it is a good question. It's another my future work. I try to study the multiple scattering problem. So yes, and this is one of my subjects. And may I introduce another subject just briefly?
Yeah, sure.
Yeah. This is more interesting because I studied the real company in my postdoc in France. The inverse scattering problem can be impossible because I have no, I cannot access the, yes. Yeah. Yes. These subjects. This subject.
Share the Zoom as well.
This is another subject, the numerical study of coupling effect or some reconstruction of the electrical field of quantum. This is the check the observation rate. SAR is the specific observation rate from the cell phone or some smart device. So I want to just introduce from this table, we can show that there are some legal limitation in each company. In Korea, we use the same limitation with the US SAR limitation. So we can also check the SAR value in this website. Even if you use the iPhone, we just from this inside in this website, we just put the cell phone number, then we can check what is the specific observation rate value. Then in this case, yes, traditional method is like this one. This is a single probe antenna. There is a machine, and we can detect the SAR value inside of this single antenna, and we can put the this liquid is some special liquid to define the real head. Then we can check this SAR value. But it is impossible to put the antenna inside human's head, so it's impossible. So there are some another approach is the non-invasive system and invasive system. Because in this traditional approach, we use only single probe antenna, because the reason why they use the single probe antenna is it is very hard to cancel the coupling effect between the probe. So there is some non-invasive, and this is my object. So invasive approach is done by this works, and I try to solve this problem by inverse scattering approach. From this expansion, single layer or layer potential expansion, and by using this complex system, we solve the inverse source problem, because it is the SAR problem is exactly same to the reconstruction solution of the Maxwell equation inside of the object from the exterior data. From the surface theorem, something like that, we only need the surface current of the object. So we try to from the data we reconstruct surface current, then we can calculate the surface current and calculate the electric field inside of it. So yes, I skip, and we consider only very simple 3D problem. Then skip. Yeah. This means that if 0.24 is the means that 24 centimeter between the cell phone and human phantom, then we have the successfully result. The error is only 3.3, something like that, only 2% or 5%. And if the closed case, we also have the result, but this shows that the distance between the error, depending on the distance between the cell phone or human head, the error is increasing. Nobody used the cell phone like this one. You should use this one. I think that this error is from the mathematical modeling. Because in my previous presentation, we assumed that the total field UI plus US. This means that UI, US, there is no coupling effect. So we need some coupling effect, some like this one, plus something like that. So yes, to improve, yes, skip. Yes, this is another my research subject, and I have also another meeting in next month, maybe. Yes, with Sandwich company, and like this.
All right. So then, for the time, let's thanks to the speaker again for a great talk.